Hello. Okay, we'll get started. So far we have been discussing about matrix exponential, which was a crucial missing link between computing solutions for linear systems. So we talked about matrix exponential. We saw some properties of matrix exponential in the previous class. Today I want to talk about the set of solutions of x dot t equals to axt, xt naught equals to x naught. So this is my ordinary differential equation. I know that we have figured out how to solve this differential equation, but I want to look at the space of solutions let me write it as ODEs. So I have a whole bunch of ODEs starting from different initial conditions. My state transition matrix, or rather the matrix A, is essentially going to remain the same. So that's not going to change, but my initial condition can be anything. And I want to look at the space of solutions of such ordinary differential equations. And I want to study that particular space. I'm going to denote that space by V. So V is the set of all possible solutions to that differential equation starting from any initial condition. I want to study this space. I want to talk about some properties of the space of solutions, and then we'll talk about some properties, or rather modes of exponential of AT, and what exactly does it mean to have a mode of a specific dynamical system. So those are the kind of topics we are going to talk about today, and in the next class we'll talk about stability of linear systems. Okay. The first theorem I want to prove in the class today. Okay, let's do a vote in the class first. So so far I think you all would agree that the solution to this particular differential equation would be so V is a subset of C R Rn. So the space of continuous functions from a real line, which is the time axis, to points in Rn. Because it's a differential equation, I'm solving a differential equation, so I know that the solution would be continuous function of time. The question I want to think about is, what's the dimension of this space V? What's the dimension? So I have a subset in the continuous functions from R to Rn. This particular set is infinite dimensional. I want to know what the dimension of V is. What do you think? No, dimension has to be a number. N? Okay, so we have an option N. What else? So dimension V equals to N. Any other vote? Yes?
You said in the prior lecture, at most N?
At most N, okay. What else? Okay, so it turns out that I was wrong in the previous lecture, and it is actually equal to N. Yeah. So the dimension of V, well, V is a vector space. Of dimension N. So there are essentially two claims here. The first claim is that V is a vector space, and the second claim is that V is a vector space. The dimension of the vector space is equal to n. It's somewhat surprising, maybe it's not surprising, or maybe it's surprising, that this is a fairly large class of differential equation because I can pick any initial condition I want. But it turns out that despite this lying in an infinite dimensional space, it actually has a dimension of n. So there are two parts of the theorem. So I'm going to make the first claim: alpha 1, alpha 2 in R, phi 1, phi 2 in V implies alpha 1, phi 1 plus alpha 2, phi 2 also is in V. So that would imply that V is a vector space. Claim 2, which is about proving that it is a vector space of dimension n. I want to find n basis vectors. And then B. So it's not really a claim. I'm going to find n basis vectors, and then I'm going to show that any solution of ODE can be written as linear combination of phi 1 to phi n. That's how I'm going to prove this particular theorem. This is theorem 3.1 in the book. Okay, how should I prove claim 1? What would you do if you were in my position, if you were the one teaching this class and you wanted to prove this statement that I'm going to pick two solutions from the set V. I want to show that the linear combination also lies in the set V. How would you go about proving this result? What does it mean for this thing to lie in the set V? It means that this one must satisfy this differential equation. I don't care about the initial condition because the set of all such ODEs, the solutions to the ODEs with any initial condition is denoted by the set V. So I don't care about the initial condition, but the dynamical equation must satisfy this condition. Okay. So what do I already know? I think what I know is alpha 1, alpha 2 belongs to R, and phi 1 and phi 2 belongs to V, which means that phi 1 dot of t equals to A phi 1 t, phi 2 dot t equals to A phi 2 t. This is given. It might have some initial condition. I don't care about it because it's part of the solution set. Okay. What do I have to do? So I have to take the derivative of this. Any questions so far? No? So I'm going to take alpha 1 phi 1 dot t plus alpha 2 phi2 dot t. I'm going to just use this expression here. This is alpha 1 a phi1 of t plus alpha 2 a phi2 of t, a times alpha phi1 t alpha 1 alpha 2 phi2 of t. So it satisfies the differential equation. This would imply that alpha 1 phi 1 plus alpha 2 phi 2 lies in the set V. So V is a vector space. I have proven that because the sum of two vectors lies in V and scalar multiple of the vector also lies in V. And right now I'm considering R. Certainly you can consider complex numbers as well. It's not going to change much. I generally, because I work in the controls area, I generally don't deal with complex differential equations. But if you were in electromagnetics area, or I don't know, you do radar design, or you do like signal processing of ultrasound images, or I don't know, all kinds of images, then you deal with complex signals as well. So I'm using everything over R, but all of this stuff works over complex numbers as well, with no change in anything that I'm talking about. Any of you who works with complex signals, complex number valued signals? No? Okay. That's a proof that nobody works in ESL from this class. And in fact, I looked at all the projects that people are trying to do in this class. Almost everyone is doing automotive related projects. Guess what the common link is? I think 95% of the class comes from Center for Automotive Research. So it was a coordinated attempt from car students to come and take this class, hence proved. Okay. Let's talk about claim 2. So I've done the easy part, which is V is a vector space. Let's do the hard part, which is we need to find the n basis vectors for for this space V, space of all solutions. Okay, so let's go back to 1800s. I ask you to find the basis vectors for the differential equations of this type. How would you come up with basis vectors for this differential equation? Yes.
Could you start with finding the eigenvectors?
Eigenvectors, that's one way to do it. What else? Eigenvectors of what? I'm assuming you are talking about eigenvectors of A matrix.
Yes.
Okay. That's a possibility. But A may not be diagonalizable, so it may not have eigenvectors. It may have generalized eigenvectors, but not eigenvectors. Anything else? Okay, so we know that x naught is in Rn. So let's consider, I want to make sure that I'm using the notation from the book. Yeah. So 2a, let x naught 1, x naught n in Rn be the basis vectors for Rn. So I pick some n dimensional vectors, and they are all basis vectors for Rn. What that means is that the span of these vectors is equal to Rn. Now, you are right. If you pick it to be eigenvectors of the matrix A, it will have some desirable properties. We'll talk about that towards the end of the class. But for now, I don't want to restrict myself to eigenvectors or generalized eigenvectors of the matrix. I'm going to assume that I have some basis vector for Rn. For all we know, we could use like the unit vectors along each of the dimension as the basis vector. And then I'm going to define phi1 of t to be phi1 of t naught equals to x01, phi2 of t naught equals to x02, and so on. And those are my basis vectors. So I start with x01 and I let the solution go. So I get phi1 as the solution to this differential equation. Phi1 dot t equals to a phi1 t, phi2 dot t equals to a phi2 t. I did it all the way up to phi n t naught equals to x0 n. Okay, so the construct is as follows. I pick n linearly independent vectors in Rn. I start the differential equation from each of those n linearly independent vectors. I get a trajectory, phi1 all the way up to phi n. What is the requirement for basis vectors? Anyone remembers what's the requirement for basis vectors? They have to be linearly independent. Okay, it's required. Basis vectors have to be linearly independent. So I know I have picked linearly independent set of vectors here, but now I have ran it through an ODE solver in order to get a trajectory, but I don't know if these trajectories are linearly independent or not. Okay, so I need to check if these trajectories are linearly independent or not. And essentially what we are trying to show is if I start with this initial condition and this initial condition and they two are in completely different directions, would it happen that the solution to the differential equation would actually merge, would collapse into the same trajectory? And the answer to that is it's not going to happen, but we need to prove it. So let's think about proving it. I'm going to erase some part. Let me erase this part. So I'm going to do proof by contradiction, the proofs that I don't like. So pick alpha 1 to alpha n in R such that summation alpha I EIT equals to 0, I equals 1 to n. So I picked a bunch of scalars such that the summation of alpha I EIT is equal to 0 for all t. What do I have to prove in order to show that this is linearly independent? Anyone remembers? So I picked a bunch of alphas. I have assumed that summation of alpha I phi I is equal to 0. I have to prove that each of these alpha is equal to 0, right? So this has to be true for all t. In particular, it has to be true for t equals to t naught. So for t equals to t naught, oh, actually, I didn't have to use contradiction. Awesome. This is because x naught I equals 1 to n are basis vectors for Rn. Okay. Any questions so far? So I picked a bunch of scalars. I assume that the summation of alpha I phi I is equal to 0. So I picked this phi I somewhat arbitrarily. I started with some initial set of basis vectors. I ran the differential equation. I got the solution. I assumed summation of alpha I phi I is equal to 0. Since it should hold true for all t, it must hold true for t naught. If it holds true for t naught, then by the linear independence of x naught I know that each of these alpha i's are supposed to be equal to 0. Consequently, phi i's are linearly independent. Phi 1, phi 2, phi n are linearly independent. So I found n basis vectors for this particular set V. Okay, can you find n plus first, like n plus 1th basis vector for this case? You know, the problem that I see is, because I only have n linearly independent vectors here, I'm only able to find n basis vectors. I'm not able to find the n plus first basis vector that wouldn't be linearly independent, right? So to some extent, I think that's the extent of the basis vectors that I can find in this space. But in order to prove that the space is of dimension n, I need to be able to say that no matter what point, what element I pick within this vector space V, I can write it as summation of the basis vectors. Okay. Okay. If that's what we have to do, then that's what we have to do. Let's see. Okay, so now to B, let's say x naught in Rn is picked arbitrarily. I'm going to pick an arbitrary vector in Rn, and I'm looking at the solution x dot t equals to axt, xt naught equals to x naught. I want to be able to write the solution to this differential equation using these n linearly independent time series. How would I do that? The answer lies on the blackboard itself, but I want you to help me. Yes, please.
Would you break up your initial condition into all of the linear basis vectors that we started with? And
Yes.
Resum
Awesome.
all the outputs.
That's exactly what I'm going to do. I had n linearly independent basis vectors. I can multiply it by an appropriate coefficient, add it up. I'm going to get the initial condition that I picked. I can always do that because I've started with a linearly independent set of basis vectors. Now, remember this claim. If I have the solutions to the differential equations for each of these initial conditions, and I'm multiplying the initial condition by alpha I and summing it up, because it's a linear system, the output xt would be summation alpha I phi t. So what we proved was any solution to the ordinary differential equation can be written as linear combination of phi1 to phi n.
Professor?
Yes, please.
So, is there a generalized way to find these linearly independent basis vectors? I think with communications, there's like Graham-Schmidt orthogonalization. I don't know if there's like a similar process to that with what we're doing.
There is. Actually, we are getting to it in a bit.
Okay.
But by the end of the class, it will be clear that there are some. The standard way to do it is if you pick the basis vectors to be E1, E2, E3, E4, which is like unit vectors in each of the directions, and that would give you what is known as right. So that would give you the state transition matrix. Okay. So that is the natural way to do it, and there is another natural way to do it which you had mentioned earlier, which is to use eigenvectors. And so we'll talk about both of those situations. So by the end of the class, we'll get a sense of what that means. Okay. Any questions so far? No? Perfect. So let's talk about definition 3.2 from the book. So I have these n linearly independent basis vectors. I'm going to call it fundamental set of solutions. And I'm going to construct a fundamental matrix. I'm going to denote it by psi, and that's That's my fundamental matrix. I want to remind you that this matrix is in Rn cross n. Okay. So theorem 3.3 in the book says that psi dot t equals to a psi t. Not too difficult to prove, because psi dot t equals to p1 dot t Okay. I also want to define another matrix called the fundamental matrix, and that is definition, no, sorry, state transition matrix. I'm going to, maybe I'll write it here. Definition 3.8. 3.8 is definition for state transition matrix. So let phi t be the solution with x naught equals to ei. So ei is the unit vector in the ith dimension. So it would look like 0, 0, 1, 0, 0. This is the ith position. And then I'm going to define my state transition matrix. Pt Okay, and one other is that that's there in the book, and I'm not going to prove it, but it's kind of easy to prove using the stuff that we will do in the class shortly. Is maybe I'll write it here. Write it as fact. Phi t naught equals to psi t naught inverse. This is the matrix inverse of this particular matrix, psi t naught. So psi t naught is a fundamental matrix. Phi t naught is the state transition matrix. And remember that xt is given by phi t naught x naught. So this is where this state transition matrix is used. That's the matrix exponential that we spent so much of time discussing in the previous two lectures. And turns out that the way this phi t naught is related to this fundamental matrix, which you got from picking some arbitrary initial condition, but like arbitrary initial basis vector, the way these two are related is by this particular identity, that phi is equal to psi of t naught inverse. So this is t naught, this is t. Okay, it's important to note the difference. This is t naught, this is t, this is phi of t comma t naught. T naught is the initial time and x naught is the initial condition. Okay, this is easy to prove, but I'm not going to prove it in the class. Okay, we have already talked a lot about what are the different properties of this matrix. We have talked about how to compute this matrix because this is the matrix exponential. So if you recall, phi of t naught is exponential of a t minus t naught. And we have talked about how to compute the exponential of at. Now, I want to talk about the. So so here is one thing that I want you guys to keep in mind. So we have been able to decompose the solution to the differential equation in terms of basis vectors, and very shortly I'm going to talk about how to think of decomposition for exponential of at. So that's one part that we haven't talked about yet. So we talked about how to compute it, but the way we computed it allowed us to compute a decomposition of this particular would allow us to compute the decomposition of this matrix exponential, which is called the modes of the system. Okay, so we are going to talk about modes of the system now. We talked about the basis for the solution set. Now we'll talk about the modes of the system, which you can view it as a basis for the exponential of at. So in order to define the modes, I want to talk about the equivalent state space representation. And in order to motivate the discussion about the equivalent state space representation, I want to ask a simple question. how is the temperature of this room measured? How do we measure the temperature of this room? There's a thermostat right there. We can change the temperature if we like, and it always gives you a reading of what the current temperature of the room looks like, and it uses that information to figure out how much cold air or hot air to pump inside this room. So my question to you is, what do you think? How do we measure the temperature of this room? Any idea? Yes?
Probably a thermocouple inside of it that gets a voltage and then tries to estimate based on knowing that it's not the entirety of the room. So it gives some lag time.
Right. I think so forget about the lag time and stuff, but what exactly does the thermocouple do? What's the physical process that drives the measurement in the thermocouple?
Looks at the two dissimilar metals, generates a voltage, and it reads back the voltage.
Certainly, yeah. So that's one way to measure it, which is you have two metal strips and they look at what the potential difference between the two metal strips is, and that kind of changes depending on what the temperature is. There's another way which is typically much cheaper, and I guess that's what they are using, but I could be wrong. You could be right. You have a resistor, and the resistor is very sensitive to the temperature. So as the temperature changes, the resistance changes, and you kind of measure what the resistance of that resistor is. Okay. So in some sense, by the way, there is another issue. So right now the temperature sensor there is reading the temperature or it's displaying the temperature in Fahrenheit. But if this thermostat was in Europe, it would be measuring the temperature in degrees Celsius. So there are three ways by which I can represent a temperature. I can use the resistance of a resistor as a proxy for temperature. I can use Fahrenheit, or I can use Celsius, or I can use Kelvin if I'm being very physicist oriented. Okay, so there are many ways to talk about temperature. So temperature is of course one, like what we call temperature, the numerical value could be quite different depending on what thing you are looking at. It could be in ohms, it could be in Fahrenheit, it could be in Celsius, it could be in Kelvin. So essentially you have a state of the system, which is the temperature of this room, and there are four different ways to represent the temperature of this room. So that's known as equivalent state space representation. So you have a state, but I can sort of massage the state a bit in order to move from one type of state space to another type of state space. And the way we typically do that is, this is my original state space. I'm going to define a new state, x tilde, which is given by P of x, or x is given by P inverse of x tilde. So P is a matrix. I'm kind of simplifying the expression here because I don't want to look into the offset. So when you go from Celsius to Fahrenheit, there are offsets. When you go from ohms to Fahrenheit, there are offsets. So I'm just doing a linear multiplication, but I'm not looking into the offset. If you wanted to use the offset, you can extend the dimension of x by 1. So you can have x comma 1, and then the offset will be part of the matrix P, and that 1 dot will be equal to 0. So there are ways to massage the expression in a way that you can get these offsets also included in the expression. Now the question is, I want to look at the differential equation in this particular space. This is an equivalent state space because I multiplied it by a invertible matrix. P is invertible. I want to look at the differential equation in this space. So let's think about it. I have x tilde dot t equals to px dot t equals to p a xt equals to p a p inverse x tilde dot t. So this is similarity transformation. Okay, so you can use, no, sorry, this should be x tilde t. Perfect. Okay. So I can pick any invertible matrix P. I can do a change of variables. I can apply this change of variables formula for this particular matrix P, and I can get the dynamical equation in the new state space. This is the new state space, this is the new matrix, and this is the new state space. What about x tilde of t? This would be given by exponential of p a p inverse t x tilde 0. What is x tilde 0? So x tilde 0 is p x 0. And this one is same as p exponential at p inverse x tilde 0. Okay, so this is the expression that is needed to prove this fact. So you can do it at home. Okay. What kind of matrix P would be desirable here? So going back to the, I mean, if I pick P to be identity matrix, then it's not quite desirable. But I can pick P to be the set of generalized eigenvectors or eigenvectors of the matrix A, and then I start getting something interesting. So what's the interesting thing that I get? So remember, T was V1 Vn, and we had T inverse At equals to lambda. So these are generalized eigenvalues. Sorry, generalized eigenvectors. And this is Jordan canonical form. And if it was the typical, the usual eigenvectors, and you have n linearly independent eigenvectors, then the matrix A is diagonalizable, and this one is just a diagonal matrix. So we talked about all those cases in the previous lectures. So I'm going to so what do I have? Exponential of At. This is something we talked about in the previous lectures. Okay, so I can pick P to be T inverse. I want to make sure I don't make a mistake. So let's take P to be T inverse. So we'll do that in a bit. We'll take P to be T inverse in a bit. But let's look at this particular expression, exponential of At. This exponential of At appears right here. And if I pick P to be T inverse, in this case, these P will get cancelled, and so you will have something which is exponential of lambda T. So x tilde T would be exponential of lambda T x tilde 0. Oh, I think I'm missing t minus t naught here. This should be t minus t naught. This should be t minus t naught. Please make a change here. This should be t minus t naught. But not here. Here I'm looking at exponential of at. Okay. What do I want to do? I want to decompose this. I want to write it as summation of exponential of lambda it times something. Either lambda it, and I just want it to be a decomposition of a scalar times a matrix. Okay, that's what I want to do. And each of this term will be called the mode. So don't copy this particular part, because I think this part is going to change depending on we are looking at diagonalizable A versus non-diagonalizable A. So the term here is going to look quite different for the two cases. But this is what we want to get to. So we have this very complicated expression. I want to write it as sum of a scalar which is a function of time times matrices that are not functions of time. Okay, so we'll get that. We'll get there. So let's look at the case where A is diagonalizable. When A is diagonalizable, lambda equals to lambda n and so we have, I want to convert it into that format. So I have exponential of at equals to t inverse exponential lambda 1t exponential lambda nt 0 t. No, t on this side and t inverse on this side. I'm assuming that lambda 1 to lambda n could be complex numbers, in which case these exponential term will contain j sine omega t and j cos omega t and things like that. But I'm pretty sure you know how to deal with those situations. Okay, so as I mentioned, I have this expression for exponential of at. I want to convert it into exponential where you have a scalar function of time times matrix. What should I do? Can someone help me? The goal is to decompose this complicated looking expression to something that looks simple, something that sum of time functions of time multiplied by matrices. And these are all scalar functions of time. These are not vector functions of time multiplied by matrices. So what should I do? Any thoughts? So this one doesn't depend on time. This one doesn't depend on time. These are eigenvectors of the matrix A, or generalized. Okay, A is diagonalizable, so they are all eigenvectors of the matrix A. So this one is not a function of time. This one is not a function of time. This is the only thing that's a function of time, and the functions of time actually appears along the diagonal elements. So any thoughts? Yeah.
So I guess it would be like you just look at your diagonal positions of t times t inverse and multiply that by exp. So it'd be like exp of lambda I t times
Right.
like t inverse t, and the just the element like I comma I.
Right. Yeah. So you are on the right track, but I want a matrix decomposition. Like I want something which is simple and easy to understand. Yeah. You have something?
You'd be able to take the exponential, split it into exponential of the is that the eigenvalue plus exponential of the time term since they're multiplied, and then break that into the sum of two matrices.
Yeah. So how do you want to break that? That's the part. I want to figure out how to break it up. So I have t here, I have t inverse here, and I have this whole bunch of things in between. So here is how I'm going to break it up. Okay. I'm going to take exponential of lambda 1t E1 transpose, exponential of lambda nt En transpose. I am so unhappy that I have transpose denoted by t, time denoted by t, and the matrix denoted by t. Such is life. Life is hard in this class. Okay. I hope you don't confuse between different t's that we'll be talking about in this semester. Okay. Does this sound reasonable? So E1 transpose is 1 here and 0 everywhere else, and E2 transpose is 1 here and then 0 everywhere else, and so on. So I can eliminate this big diagonal matrix by writing it in this particular fashion. So what I get is summation exponential lambda it t ei transpose t inverse. I goes from 1 to n. So you can think of these. So these are known as modes. Modes of the system. Let me check if modes include the, I think modes include the matrix as well, but I want to make sure. Right, it includes the matrix as well. So all of this included. So I have n modes of the system. Each mode has a matrix multiplied by exponential of lambda it. So if you go back to Professor Serrani's notes that are available on Carmen, he has done it for 3 different cases. When lambda is real, when lambda is complex, he has like some other modes of the system, and when lambda has Jordan canonical form, he has some other modes of the system. So I'm just going to do it for the diagonalizable case and the Jordan case. I'm not going to do it for the case where you don't want to use complex numbers here. Ultimately, you get the same solution, but anyways, there are different ways to write these modes of the system depending on what viewpoint you want to take. So in this mode of the system, the way I have defined is lambda I could be complex, t could be complex, ei is not complex, but this t inverse could be complex. But overall, you will get the same solution in terms of the value for exponential of at after cancelling out all the j omega and minus j omega terms. Okay, so these are known as modes of the system. And now if I have a solution, I want to give it some name. In the book, they call it AI, I think. Let me make sure I have that page open. Right, so this is AI. So I'm going to write xt equals to exponential of at x naught let me write dot x dot t equals to axt x0 equals to x naught. So my t naught is equal to 0. I don't want to carry t minus t naught everywhere. So I've just made that simplification. And I can write this as summation exponential of lambda it. I goes from 1 to n ai times x naught. So the modes gets multiplied by the initial condition, and that gets you the how the overall system xt is going to behave as a function of time. The book uses some other forms of derivation. We are not using that in the class. I want things to remain simple and easy to understand using just matrix manipulation. So if you read the book for the derivation, you will get confused because we are not covering that way of doing it. So the book is using Laplace transform to come up with the modes of the system. We are not using Laplace transform at all here. Okay. You know, the cool thing, when I write the expression in this particular format or the solution to the differential equation in this format, is now I know when are things going to get amplified when lambda I is positive or it has positive real part. In that case, things are going to get amplified and that part of the state is going to blow up. And when lambda is negative, then this term is going to go to 0. And so whatever initial condition you have, those initial conditions, I mean, that particular mode will converge to 0 very quickly. So if ai times x naught is positive for lambda I positive, then your system is unstable. We have not talked about stability, but you can imagine that xt will go to infinity. On the other hand, if ai times x naught is equal to 0, then even if lambda I is greater than 0, your system will not have any instability, nothing will go to infinity. And you can have like you can come up with similar arguments when lambda I is negative. Ideally, we want to create structures, we want to create systems where all of these lambda i's are negative so that the systems are stable, and no matter what disturbance you have at time 0, all of those disturbance decays exponentially. Whenever lambda I will have complex numbers, which means that you will have non-trivial imaginary part, then you will see oscillations in the system. Okay. So remember we talked about the bridge example a few days back. We showed you like the picture or rather the video of the bridge, Tacoma Narrow Bridge, which collapsed. So you can imagine that it has one of the modes that was unstable to perturbations from the airflow, constant wind, and that led to the collapse because the wind injected energy into the system. That energy was amplified because of the positive eigenvalue, and so the bridge collapsed. Nowadays bridges are built so that they have negative eigenvalues. So they do this analysis even before the bridge is constructed. They do the analysis of the bridge using different civil engineering softwares, and they make sure that the dynamic modes of the system are all stable. When they create tall buildings, I showed you a video of tall buildings. They put actuation within the tall buildings in order to make sure that the modes are stable. Um, are there benefits to unstable systems?
Yes.
Yeah. What's an example of a?
I'm pretty sure every fighter jet in the last like 30 years is unstable.
That's right.
Yeah.
So fighter jets are unstable. Fighter jets are unstable. Why are fighter jets unstable?
Because they can turn faster, and now
That's right.
Computer controls, you can
Right.
control the computer.
That's right. So fighter jets are unstable by design because they want very high maneuverability. But passenger jets are stable by design. So even if both engines die out, the plane can just land without any engine thrust. Any incident you remember of plane landing down without the engine? No? Yeah. there was a Hudson River incident. I don't know how many of you remember. It happened in 2011, 12 maybe. And so there was a bird hit into the engines, and so the flight did not have any thrust, and so the pilot landed that particular plane on Hudson River, okay, in New York. So that was the case where all the modes were stable, so all the lambda i's were negative, as a result of which the plane could land. If that happened to a fighter jet, it's not possible to land it. It's unstable by design. Another trick question. So I'm sure many of you might have flown a plane or might have seen videos of the plane. When you are walking around in the plane, what's happening? Is it becoming stable or unstable? The way to make a plane unstable, a passenger plane unstable, is you ask everyone to go in the back of the plane and just stand there. Okay, so that way the plane will become unstable. On the other hand, if everybody is coming to the forward, then the plane is generally stable. Or maybe the other way around, I don't know. But if you move the load in the plane in a certain way, like either all the load in the front versus all the load in the back, it's becomes stable versus unstable. Okay. So whenever the pilots are saying that please don't congregate in the back or congregate in the front, there is good reason why they are saying that. Okay. So that's about the modes. This is the case where A is diagonalizable. Things are very simple and straightforward, and we can decompose. We can look at the modes of the system. Now let's look at the other case where A is not diagonalizable, which means that lambda now is in a Jordan canonical form. Okay. So let's look at case 2. I'm going to do the simple case. Because the more complicated case would be kind of I won't give it as a homework, but you can do it at home. So I have all the same eigenvalues along the diagonal and 1, 1, 1 along the off diagonal term, and then 0 everywhere else. So that's the case I'm going to do. So exponential of AT, as written previously, it's T exponential lambda T inverse. Okay, what should I write in this part? What is exponential of lambda T? Anyone remembers what the exponential of lambda T was? Can you check what is exponential of lambda T from your notes? I think it had something to do with exponential of the diagonal part multiplied by exponential of nt. So I think this one was equal to exponential of lambda it times exponential of nt. Do you have this expression in your notebook? Okay, we did that a few days back. Okay, so what is exponential of lambda it? This is exponential of lambda t, and then I have exponential of nt. Okay, exponential of lambda it is just exponential of lambda t times identity matrix, but whatever, identity. Is it exponential of lambda t times identity? Let me think. Yeah, I think it is. Yeah, it is that exponential of lambda t times identity. So identity multiplied by exponential of nt is exponential of nt. So this is what the exponential looks like. So I'm going to write that as exponential of lambda t plus exponential of lambda t t n times nt. Right, I can write it in that fashion. I think the last term is going to be exponential of lambda t n raised to n minus 1 t raised to n minus 1 over n minus 1 factorial. That's going to be the last term in this expression. So what do I get? I get summation I equals 1 to n or maybe I should use I equals 0 to n minus 1. It will be easier like this. I'll have t raised to I exponential of lambda t times t n raised to n minus n raised to I t inverse over I factorial. So I have n modes of the system, which looks like this. So this is the term that depends on time, and this is the matrix. And these are the modes of the system. Once again, you will see the same thing. If lambda is positive, then this term is going to go to infinity. If lambda is negative, this term is going to go to 0. So remember, t raised to I goes to infinity as t goes to infinity, but exponential of negative times t goes to 0 much faster. Therefore, the multiplication of these two will go to 0 if lambda is negative. And if lambda is complex, then you will have oscillations you will have oscillations in an appropriate sense, because those magnitude of those oscillations will get multiplied by t raised to I as well. Okay, so if your system was not diagonalizable, which means that you have Jordan canonical form, then the modes of the system will be given in this particular fashion. This is the case when you have the same lambda along the diagonal. Now, of course, in the general case, your lambda would comprise of some diagonal terms, some complex terms along the diagonal, and then you will have some Jordan canonical forms along the diagonal of the matrix. And so you will have to compute the modes of the system appropriately. And hopefully, whatever system you are creating, assuming that the design requirement is to make sure that the system is stable, you want to make sure that around the equilibrium trajectory, you compute this A matrix by computing the Jacobian of the nonlinear system, and then you compute the modes of the system, and hopefully the modes of the system are stable, in which case you have a stable system. So whether you are designing suspension of the next generation of luxury vehicles, or you are coming up with a battery thermal management system, or you are designing nuclear power plants, you want to make sure that the modes of the system are stable. What that means is this lambda should have negative real part. Any questions so far? Okay. So when we wanted to solve the problem, whenever we are trying to solve this particular problem, so what is it that we are looking for? So we want to compute the solution of this differential equation from a given initial condition. We realized that we need to compute matrix exponential to do that. So we figured out how to compute the matrix exponential, and using all the stuff to compute the matrix exponential, we identified what the modes of the system are going to be. And then we realized that actually it's the modes of the system multiplied by matrix multiplied by initial condition. So remember, this implies that xt equals to summation modes ith mode multiplied by x naught. That's what the solution looks like. I equals 1 to n. That's what the solution is going to look like. So as long as each of these modes is stable, it's going to 0. You will have no problem with the initial condition. If these modes are going to infinity, you might have a problem, and you want to make sure that you don't have any such modes in your system. Okay. So that's the discussion on modes of the system. In the next class, I want to talk about the input output. We'll spend a little bit of time on the input output characteristics of the system, because what might happen is even if you have unstable modes of the system, you may not be able to observe the output, and therefore you may not be able to know that you have an unstable mode in the system. So those of you who have seen Teslas on fire, or maybe I shouldn't use the word Tesla, those of you who have seen electric vehicles on fire in LA or in many of the hot cities around the country, it's because there are modes of the battery thermal management system, and for some reason those modes were unstable, but it was not observable, so you couldn't control it. And when the battery pack burnt, it means that you saw one of those unstable modes, and things went to infinity. So anything whenever state goes to infinity, it means there is some problem, there is undesirable characteristics in the system. So when they saw it, then they realized that they need to change the battery management system, they need to change the thermal management system, they need to have more sensors in the battery to be able to measure the unstable modes of the system in case instability arises, and then take appropriate actions in those cases. And that's how they were able to create, by better battery management system and better thermal management system and so on, they made sure that all the modes of the system are stable. But there is one situation where you don't quite control the modes of the system very well, which is in the case of an accident. So if you have an accident and you have a battery, and if there has been any punctures in the battery due to the accident, it's not very clear what the unstable modes or stable modes of the system is going to look like in that particular situation, because then the dynamical behavior of the system has completely changed post-accident. So again, something to keep in mind, something that, because most of you are coming from Center for Automotive Research, you need to keep in mind that these whole discussion of modes is very important from a safety standpoint. And if I'm assuming many of you will go into EV industry, because that's the industry that's hiring a lot of people, you will have to think about modes of the system during the normal operations, modes of the system in like desert operation, if you are in Nevada or if you are in Colorado desert and so on. You need to make sure that the modes are stable, and you will have to think about modes of the system post crash, after the vehicle has crashed and the battery pack might get punctured. How exactly do you want to control, how do you want the battery management system to function, so that even under punctures you still have a stable operation mode. So something to think about and keep in mind for the future. That's all I have for today, and we'll meet again on Thursday, and we'll talk about input output behavior, and we'll talk about the stability of the system. Thank you.